Hi, this is Jeremy Comel, CEO of Innovative Omics and research faculty at Yale, working closely with Crystal Pollitt's lab. And today we're going to be discussing, once you've run your PFAS NTA analysis using Agilent Explorer, generated PFA project file and imported into FluoroMatch and run FluoroMatch, now you have an integrated results that both has all the value that Explorer gives you in terms of NTA analysis and all the value that FluoroMatch gives you for PFAS analysis as well. And all of this information is now contained in this visualizer platform, and we showed you how to upload it in the previous video. So I want to show some of the unique aspects of Agilent in a visualizer, but first I'll go over the basics. So we have a Kendrick mass defect plot, and in a separate video under our tutorials we talk about each one of these plots. So if you're unfamiliar with what a Kendrick mass defect plot is, retention time versus mass charge plot, Kaufmann analysis, please see that video that we'll also put in the description section. Now your visualization is filtered by scores, with A being those that are database matched to our database of over 10,000, not nearly, I think 15,000 now, PFAS molecules and their fragment rules with less than 5% false positives. So these are going to be our bread and butter, very confident annotations. B+ also very confident, but don't meet all the criteria of which fragments need to be observed. And so right away in your data set, if you have high confident PFAS, depending on how complex your matrix is, you should see some interesting patterns already. Note this is AFFF contaminated soil, so don't expect to see this many PFAS if you're running blood, urine, etc. You won't. But you will still be able to discover other unknowns. Now let's look, you can either look series-wise. So for example, if I wanted to click a series, now I can see all those members in a series, looking at their patterns, both in retention time, mass, and charge, across Kendrick mass defects, see their average MSMS, see their fragments, so on and so forth. But let's focus on an individual molecule. So let's focus on, for example, we're going to scroll through here. You can see all the different classes that were annotated. And let's look at the PFC perfluoroalkyls. So here shows some of those molecules that were annotated as perfluoroalkyls. And if we select on one, you can see it's Agilent ID. So this is Agilent ID 76. So we can now pull out Agilent ID 76. And this is a unique aspect of the Agilent ID integration, only available if you run the Explorer workflow. So let's unselect PFCA, and what we'll find, and also unselect our scores, and what we'll find here is that you can see the molecule. So this is the molecule of PFCA and any other adducts. So this is the 2M-H. So for example, if we wanted to look at PFOA, we could also see the molecule plus any other adducts. And so now you can see these patterns that start to form with the 2M-H species. Now Agilent automatically combines all adducts, in-source fragments, etc. We talked about in the Explorer how you can set which ones you look for. But if you wanted to verify, you could look at the EIC and see that the EIC of the parent is the same as the EIC of this case of the dimer, and that they overlap very nicely. You can also look at the deconvoluted MS1 spectrum And here you can see all the annotations of all the isotopes as well that were pulled out by Agilent. And then you would see all of those isotopes as well for the 2N-H. So for example, if we zoom in just to make it a little clearer, here you can see all the isotopes as deconvoluted by the Explorer workflow. Now the real advantage here is that you get an incredible formula prediction using the isotopic deconvolution across many samples that Explorer does. When you export that to a PFA project, FluoroMatch reads in those deconvoluted MS1 spectra and uses 12-step formula prediction as developed by David Schiesel, who works also with Innovative Omics. You can see in this case the formula prediction is correct for the top-ranked molecule, that the score is much higher than all the other possibilities, although we can go through and see how the isotopic patterns match for other possible hits. Another aspect of the PFA workflow is that we also get the MSMS. So in this case, let's look at one of the species hits. Let's pull out another compound for some diversity. So we can undo all of our filters. And this is what our entire data set would look like. So if I unselect here, now you can see all of the molecules that were picked out by the Explorer workflow, all those features and their respective adducts, dimers, etc. You can also pull out specific adducts that Agilent was able to detect. So in this case, 2N-H and N-H were the only ones used in the Explorer workflow, but we also know that we can see the loss of HCO2, etc. If we add those to the Explorer workflow, which we do recommend. So let's pull out pentafluorosulfonic acids. I believe if we look at PFSA and we have a pentafluoro over here, we can see based on these circles are based on the concentrations, again from the Explorer workflow, those peak areas. So if we select one of those molecules, now you can see the fragmentation and you can see how helpful this fragmentation can be. So here's all of the different chain lengths with the sulfonic acid, showing indeed that it must be a sulfonic acid perfluorinated molecule. And then we also see the pentafluorosulfide. You can see the fragments in this table as well at the lower mass range. So both the sulfonic acid related evidence and the pentafluorosulfide evidence. Now, beyond MSMS, EICs, isotopic patterns, formula prediction, we also can look at Kaufmann space. So again, I would highly advise you look at the tutorial videos in the description to understand Kaufmann space and how it's useful. But generally, all these blue markers are PFAS and their theoretical values from the EPA master list. And as you can kind of see, this little blue dot is within Kaufmann space, meaning it's likely a PFAS. If we include all the members of the series, we can scroll down too and see all of them fall nicely within Kaufmann space. One last thing I do want to show as well is formula prediction for a series. So here's the pentafluorosulfides, which have the CF2 chain and SO3 and end in SF5. So you can see the subclass here, and you can see the formula prediction across for all of these members of the series. You can also see that the formula predictions themselves, the individual ones, were quite accurate, with only one being incorrect. And what homologous series does, or 2 here being incorrect, out of 1, 2, 3, 4, 5, 6, 7. So quite accurate formula predictions, but even to be more accurate, when you have a homologous series, what it does is it will leverage all of these molecular formulas for the same series and say which subclass occurs most across predicted formula. So in this case, you're going to have your pentafluoride fluorosulfide sulfonic acid subclass as the one that dominates, and then it predicts the rest of the formulas using that subclass. And this approach is a 0% false positive formula prediction, especially when integrated with the Explorer workflow, because as you remember, the isotopic deconvolution done by Explorer across many samples that we integrate leads to much higher isotopic fidelity than if you were to use the raw Agilent files themselves in the FluoroMatch flow version. So there's a lot more to cover in this visualizer, but we'll leave annotation for the next tutorial, how to validate and discover unknowns. I just wanted to give an in-depth overview of some of the features available, especially highlighting some of the new features that integrate the Explorer workflow and the PFA project files. I do also want to mention that these MSMS spectra are from the PFA project file as well. So these are pulled out from Explorer and deconvoluted by Explorer across all your samples as well to give a high quality MSMS spectra that we can use for annotation.